Well, good morning, everybody. Hope you had a wonderful Thanksgiving break and welcome back to the last little bit in November and maybe even the beginning of December, depending on when you're watching this. Hey, wanted to go over the calendar with you, give you a sense of where we're at right now, and talk about what we're going to do moving forward. So you should have already by now turned in the periodic table lab. Either you turned that in last time before Thanksgiving. If not, then you should have had a couple minutes before starting this video to turn this in before class starts. So periodic table lab should be submitted and we're ready to move forward. So what you're going to see is if you're in an A day, we're here. If your B day, of course, will be on Tuesday. But we are going to spend the remainder of this unit talking about the structures of molecules. Today we're going to build on the things that you learned last time or in the last unit, drawing Lewis dot structures. And we're going to start drawing Lewis dot structures not for individual atoms, but for molecules. So that will be today, and then if you're a B-Day student, that will be tomorrow. Then guys, coming back after that, we will talk about what these molecules actually look like three-dimensionally, and we'll be getting into a little bit of that, building on the things that we learned about Lewis dot molecular structures. So you'll be learning about Lewis dot structures today. That homework will then be due on your A day or B day here. Then we'll be talking about geometries. This will move us into the last lab of the unit and of the quarter, the year actually. And you'll be given model kits, and you'll actually be building the molecules that you drew the structures for the previous couple class periods. Then guys, they promise me that December 9th will be my last day of quarantine, which means I come back just in time for you guys to take a test. Understand, I think this is going to be totally fine. Guys, the material that we're going over right now really does transfer well to this learning format. Again, if you have questions, please don't hesitate to reach out to Miss Call. She's super available, especially after school. I'm an email away if you need me as well. So guys, please continue to stay engaged, and let's end this quarter well. So again, I'm out of quarantine the 9th, which means I will see you the day of the test. So we can look forward to that. So again, you need to gather up some materials. You are going to need certainly a periodic table and some note-taking materials. You should have already gathered those things up. And why don't we go ahead and get started? So let me close this and let me move over here then and grab what we're talking about today. And let's pause for a second and let you get started. So guys, the topic for your notes today is Lewis dot molecular structures. If you're interested in dating your notes, frankly, I'll leave that up to you because I'm not exactly sure when you're watching this. But again, what we're going to do is we're going to build on the ideas that you learned in the previous unit about how to draw Lewis dot structures, and what we're going to do is we're going to be drawing these Lewis dot structures for molecules rather than atoms. So pulling this back together, in a previous day we learned about these ideas of different types of bonds, and we talked about there being ionic bonds, that ionic bonds involve a strong nonmetal and a weak metal getting together, and the nonmetal steals the electrons from the metal, and those create ions which then bond together to create salts. We also talked that day about metallic bonding and this interesting idea that these metals are all large and fat and weak, and they lose electrons readily, and when they do, all of these electrons end up moving around throughout the entire substance, and we describe that as being a sea of electrons. And then we also talked about covalent bonding. But before we do, guys, understand that we are done with ionic and metallic bonding. We have done all that we're going to do with this. And for the next actually 3 class periods, we're going to be looking specifically at covalently bonded structures. We understand that covalent bonds form when 2 nonmetals get together. We remember that nonmetals are on the right-hand side of the periodic table, which makes them small and therefore strong. And we remember that when these nonmetals get together, they wrestle over these electrons. And as they wrestle over these electrons, neither one wins, so they share. And that forms what we call molecules. And what we're going to do today then is we are going to figure out what these molecules actually look like. We're going to get started today. We're going to get an even better idea of what these things look like next time as we look at their actual 3-dimensional structures. So moving forward then, guys, what we need to do is do a brief review of Lewis dot structures. You don't need to write these questions down, but certainly the answers to these questions are things that you should be familiar with. So question 1, which electron dots appear in Lewis dot structures? And we understand that the dots that appear are valence electrons. These are the electrons that are on the outside of the atom, and it makes sense then that these are the ones that interact with each other because they're the ones that are on the outside. Then, how many of these dots can there be in a Lewis dot structure? And we remember that there can be 8. The reason that there are 8 is because these electrons exist in the highest S and or P sublevels. And as we break those sublevels down, we understand that these 8 electrons are distributed within these sublevels. There can be 2 in the S sublevel, there can be 6 in the P sublevel, and as a result, that gives us a total of 8 electrons. Now, it's important for us to remember that these electrons are in orbitals, and we remember that there is one s orbital, and that this orbital is a sphere, and that there are 3 p orbitals, and these orbitals are dumbbell shaped. The spaces are really not important, but it is important that we remember that there's 1 s orbital and 3 p orbitals, giving us 4 total orbitals, and therefore space for 8 electrons. This then leads us to an idea that we've been sort of talking our way around for some time, but it's time now to finally bring a sharper point to it. And it's called the Octet Rule. This is worth including in your notes. Guys, this is a guiding principle for figuring out how atoms interact with each other. So when we talk about the Octet Rule, not surprisingly, the root of octet is the prefix oct, which you probably know means 8, which shouldn't be a surprise because there are 8 valence electrons. And the Octet Rule then simply says that when atoms bond together, they are most stable when they have a complete shell of 8 valence electrons. And some of you may be thinking ahead and realizing that 8 valence electrons gives them then the electron structure of a noble gas. Please remember that this doesn't mean that they become noble gases, because that's determined by the number of protons in the nucleus, but they do in fact take on the electron structures of the noble gases. Okay, so in order to get started then with drawing Lewis dot molecular structures, the place to begin is by drawing Lewis dot atomic structures. So what I'm going to ask you to do, and please do this in your notes, draw the Lewis dot structures for these 5 elements. We will pause the video for a second to allow you a moment to do that. Once everybody's ready to go, we will move into this, and please do them with the spacing and order that you see on the screen, because there's one little tricky bit that we need to talk about. So if you would pause the video for a second, draw these Lewis dot structures, and once we're all done, we'll get back together, restart the video, and take a look at the answers together. Okay, now that you've had the opportunity to draw these Lewis dot structures for yourself, let's go back and look at these and make sure that we're all clear. So hydrogen is in the first group, of course, on the periodic table. It's an alkali metal, and it has 1 dot. Guys, please remember, it doesn't matter where that dot goes. It could be top, bottom, left, right, really doesn't matter. We just need to remember that it has 1 dot. Now, with that said, here's an interesting idea that we're going to start talking about. Again, something we've referred to, but you'll notice that hydrogen has this 1 electron right here, and then it's got a space next to it. This space, and you could write this down in your notes if you need, this space denoted by this red box right here, this space is actually what is called a bonding site. This is a place where another atom can come and share an electron and create a covalent bond. So anywhere we have 1 electron but not a second paired electron, we have what's called a bonding site. So with that idea in mind, let's move along to nitrogen. So as we look at nitrogen, nitrogen is in the 5th group, and therefore nitrogen has 5 valence electrons. Notice that the first 2 are paired in the S, the remaining 3 are unpaired in the P. And it's important that we remember that those 3 electrons are unpaired. The reason that that's important is we can now see that nitrogen has 3 bonding sites. If we had paired these electrons together, it would have only provided us perhaps 2, but spreading those electrons out in the P sublevel, we see that nitrogen has 3 bonding sites. We're going to find out soon that that means that nitrogen can form 3 covalent bonds. So moving along then to oxygen. Oxygen has 6 valence electrons. Spreading these out, we end up with 2 in the S and then 4 in the P. One of those P electrons has to pair up, leaving oxygen then, as you probably see, with 2 bonding sites. Moving to chlorine with 7 valence electrons, you might then see that chlorine has 1 bonding site. Now you'll notice that as we went through doing these, we actually skipped over carbon. And there's a reason, of course, that we skipped over carbon, because carbon's a little bit interesting. So looking at your Lewis dot structure for carbon, you should have had this. The carbon has 4 valence electrons. The first 2 are paired up in the S, and then the P electrons are spread out like so. And looking at this, we might guess that carbon has 2 bonding sites. Well, it turns out that's not the case. So little change for you here. When we draw these Lewis dot structures, guys, we're going to change the rules a little bit. And we are going to spread out the electrons in the Lewis dot structures as much as we possibly can. So those 2 electrons that are paired up in the S, we are actually going to spread out, and we are going to draw them separated like this. Now that we've separated those 2 electrons in the S, you'll notice that this provides then carbon with 4 bonding sites. And guys, what we're going to find out is that that is the maximum number of bonding sites. Carbon can form 4 bonds. That's the most bonds that any element can form, which is actually why we are carbon-based life, because life is complicated. In order to create complex molecules, we need atoms that have lots of options, and carbon is the element that has the most possible bonding options, and therefore it's a great choice if you're trying to build complicated life-based molecules. So what we're going to do now with this idea that we're going to spread out these electrons is I'd like you now to please go back to your other 4 drawings, hydrogen, nitrogen, oxygen, and chlorine, and redraw those by spreading out the electrons. Go ahead and go back and do that. We don't need to pause the video. I'll wait for about 15 seconds. It shouldn't take you long, and then we'll look at the answers. So spread out your electrons in the other atoms. Okay, I'm back. And obviously I didn't wait for 15 seconds or so because I think most of you, some of you, actually probably caught on to the trick. Redrawing all the rest of these atoms doesn't change anything. if we try to spread out the electrons, for example, in nitrogen, we could pull one of these electrons out of there, place it here, and we end up exactly where we started. We end up with one pair of electrons, three unpaired electrons. Even more so here, we pull an electron out of there, we pull an electron out of there, and we end up exactly where we were before, two pairs and two unpaired electrons. Obviously here we can pull this electron and move it and nothing changes. So that's the reason why we used carbon as the example of this, is because carbon is actually one of the only elements where it actually makes a difference. And therefore all the other atoms don't really change, and we just need to keep this in mind when we talk about carbon. Okay, so again, quick review of drawing Lewis dot structures. And we are now ready to start talking about how to draw Lewis dot molecular structures. So this is not stuff that you need to write down. I simply want to show you where it is we're headed. I'll show you a simple example. Then I'll share with you some rules to make these even easier. And then we're going to do a few together, and then you're going to have time to work on your homework. So for example, let's take the Lewis dot structure of oxygen. Looks like this, and we've already identified that oxygen has two bonding sites. These bonding sites are places where other elements can come and place their valence electrons and create bonds. And so we could take, for example, a hydrogen atom. You'll notice that hydrogen has a bonding site here, that oxygen has a bonding site here, and these then lock together like puzzle pieces. And when they do, we end up with a covalent bond forming. That bond is formed here in that shared pair of electrons. Well, I know that you see where this is headed, but oxygen obviously has another bonding site, and we end up with a structure that looks like this. Now, this is actually not how we are going to draw our Lewis dot molecular structures. I know that you see that this is water, but if you look very carefully at these shared pairs of electrons, these doubled up guys, we are not going to draw those as dots. We are going to replace those dots. Again, guys, watch carefully. We're going to replace those dots with lines. Those lines represent what are called bonding or shared pairs of electrons. That's a term that you need to know, but we'll use it in context, and I don't think you need to write it down. So you'll notice that here we have two bonding or shared pairs of electrons. Well, what about these electrons over here that are not involved in bonding? Well, they have names as well. They are actually what are called non-bonding or lone pairs of electrons. And so we would say then that in a water molecule, the oxygen has two bonding pairs and two non-bonding or lone pairs of electrons. Now, because what you're going to see is that we could draw Lewis dot structures for all of the molecules that you need to know by literally doing this, drawing the Lewis dot structures for the atoms and locking them together like puzzle pieces. But that's actually not what we're going to do, because I'm going to teach you to draw these molecules in a way where it's not necessary to draw the Lewis dot structures for each atom every time. And to do that, we're going to take advantage of a couple shortcuts. Now, guys, understand that these shortcuts work so long as you actually keep these shortcuts in mind. So these are worth writing down. So let's talk about these shortcuts. We are going to call these helpful steps. And we will list these out. They are actually steps. So this is how to draw Lewis dot structures step by step. When you get to college, you may find that you have professors that teach you to draw these by drawing the Lewis dot structures of the atoms first. But guys, understand what I'm about to teach you works, and you could certainly use it in the place, and you're going to find this much, much easier. Okay, so here we go. Step number one, again, encouraging you to write these down. Step number one is this: put all the atoms on the paper and then single bond them all together. Once again, put all the atoms, quote, on the paper and single bond them together. So that's step one. So what about the helpful hints? Well, as you do this, the first thing that you need to keep in mind is you need to draw these symmetrically. Many of you probably know that the word symmetrical means balanced or the same on both sides, but let me show you quickly what that looks like. Don't write down the example, just check this out. So guys, for example, the molecule NO2. We could write NO2 like this. It even seems to be the way that it's written here, 1 nitrogen, 2 oxygens. And when we take 1 nitrogen and 2 oxygen, we get 1 nitrogen and 2 oxygens, and it looks like so. The trick here, though, is that this is not balanced. It's not symmetrical. Writing it like this actually makes the molecule symmetrical, and this is the preferred way to do this. So when you draw molecules, draw them symmetrically. Another helpful hint, when you draw these, guys, always put carbon in the middle. Carbon, again, is an atom that has a maximum number of bonding sites, loves to be in the middle. So if you got carbon, put it in the middle. Now, helpful hint number 3. Guys, you're going to forget about this. You're going to blow this off. You're going to ignore this. And if you start getting these wrong, it's probably because you're ignoring this rule. The rule is this: halogens and hydrogen can never be in the middle. So let's talk about why. So remember, the halogens are in group number 7. An example that we looked at is chlorine. And then, of course, we have hydrogen. Well, we've already established that chlorine has 1 bonding site. Hydrogen has 1 bonding site. And guys, because of this, these atoms can't be in the middle. We can create 1 bond here, but there's nowhere else to bond, and therefore chlorine and all the halogens and hydrogens can't be in the middle. They're the caps at the end of a chain, but they never go in the middle of a molecule because they can only form 1 bond. Then as these get more complicated, many times you'll see that the bonding order is actually given in the formula of the molecule, and we'll talk more about that later. Okay, so there we have it. Put them all on the paper, make them symmetrical, put carbon in the middle, put halogens and the hydrogens never in the middle, and then many times the bond order is given in the formula. Now step 2. You're going to count up all the valence electrons for every atom, and you're going to watch out for ions. Just write it down for now. It'll make more sense in a minute. Okay, now we're on to step 3. We've got them all on the paper. We've kept an eye on those 4 helpful hints. We've now counted up all the valence electrons. Now step number 4 is we are going to spread the unused valence electrons evenly around the molecule. And again, I know that doesn't mean a lot to you, but it will. So spread the unused valence electrons evenly around the molecule. Now, as you do this, a couple hints. First of all, well, actually 1 hint, make sure you fill the halogens first. Again, in a previous hint, we established the idea that halogens can never be in the middle. Because they can never be in the middle, they can only form 1 bond, which means that all the rest of the electrons around the halogens have got to be placed as soon as that 1 bond is formed. So always fill the halogens first. Then, once you've done that, the last step is to check and fulfill octets by creating multiple bonds if necessary. So there you have it. There's your steps. These 4 steps every single time. If you find that these are getting difficult for you, do the steps. Step number 1, put them all on the paper. 2, count up all the valence electrons. 3, spread the unused electrons out. We'll talk more about that in a minute. And then finally, check the octet rule and make multiple bonds if you need. Okay, so with those in mind, we are now going to look at 4 examples. This is also what your homework is going to look like. And so it simply goes like this. You are going to draw the Lewis dot structure for NCl4, and then we're going to count the number of shared and lone pairs. So let's go ahead and get started. So again, following our steps, step number 1 is to get all of the atoms on the paper. But we are going to do this remembering our hints. And guys, here's hint number one. Chlorine can never be in the middle. So if we do this, we're already in trouble because chlorine cannot be in the middle. So how are we going to get all of these on the paper? Well, nitrogen is the only one that can be in the middle, and then the chlorines have got to surround it. Now guys, here's the trick. Up, down, left, and right doesn't matter. You just need to put them on either the top, the bottom, the left, or the right. Not on the corners, not diagonally, but where these go doesn't really matter. So step number one is done. We've got them all on the paper, and they're all single bonded, and chlorine is not in the middle because it can't be. Now step number two is to count up the valence electrons. And so this is just like dots in Lewis dot structures. Chlorine has got 5. If you're not sure why, go back earlier in your notes and look not chlorine, nitrogen has got 5. And if you go back and look in your notes, guys, when we drew Lewis dot structure of nitrogen, it had 5 dots. It's in the 5th group. Then chlorine, remember, has 7 dots, but there are 3 of them for a total of 21. So we've got 21 valence electrons from 3 chlorines, 5 valence electrons from the nitrogen. We add all of those up and we get 26 valence electrons. So that's the total number of valence electrons that we have to play with. But we've already used some. We've already created some bonds. So if we go down here and look at what we've already done, we've already created 1, 2, 3 bonds. And guys, if we remember, each one of those bonds represents 2 electrons. So if we go back now, we have actually already used 2, 4, 6 valence electrons. So we've already used 6, which leaves us a total of 20. I'm going to clean up my mess a little bit there by getting these circles out of our Lewis dot drawing. Well, it's not going to let me, so let me just clean this up a little bit. Okay, so there we go. And we've already used 6, and that leaves us a total of 20. So that means we now need to get these 20 valence electrons around this molecule. And looking at step 3, we spread them evenly around the molecule. But remember, guys, we fill up the halogens first. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so now we've got the halogens all full. We used 18 of the 20 electrons that we have. So we've got 2 left, and we're going to put those on the nitrogen. All right, so now we've used up all of our 20 electrons. So now what we need to do is check the octet rule and make sure that everybody's happy. So I'm going to draw for you what I'm looking at because you don't need to draw this, just visualize. So we're going to start with the chlorine that's on the left. And looking at the chlorine that's on the left, that chlorine has got 8 electrons around it. We've got 1, 2, 3, 4, 5, 6, and then that line represents 2 for a total of 8. So guys, that chlorine has got 8 electrons. It fulfills the octet rule. So now let's look at the chlorine down at the bottom. So if we look at this chlorine and if we draw an imaginary circle around it, we can see that this chlorine has got 1, 2, 3, 4, 5, 6, and that line represents 2, 7, 8. So it's got 8 electrons. So now let's look at this chlorine and drawing an imaginary circle, visualizing a circle around this chlorine. This guy's got 1, 2, 3, 4, 5, 6, and that line represents 2 for a total of 8. So that chlorine's good as well. Now what about the nitrogen? Because if we draw an imaginary circle around the nitrogen, check this out. If we do that, we've got 1 and 2, but then 3, 4, 5, 6, 7, and 8. Notice that those bonds count as 2 electrons for each of the atoms. So nitrogen has 8 electrons around it as well. Everybody's got 8, and we're happy. So what if they don't all have 8? Well, we'll talk about that more in a minute. So now, guys, we just need to finish this up, and we need to count shared and lone pairs. So to do this, I'm going to switch colors. Let's go with yellow because that's going to stand out. And we need to count shared and lone pairs. So here we have 1, 2, 3 shared pairs of electrons. So there's 3 shared pairs of electrons. Then here we've got 1 lone pair of electrons. And now you're saying, wait a minute, what about all these other lone pairs all around this molecule? And guys, when we do shared and lone pairs, it's only around the central atom. So that would be 3 shared and 1 lone pair. Okay, so there we did NCl3. Again, 4 steps. Let's try a couple more examples. So cleaning this up, let's switch pages. And let's try C2H4. Okay, so the first thing that we're going to do with C2H4 is we are going to get everything on the paper. Now remember, we have rules. Carbon is always in the middle. Hydrogen is never in the middle. So how are we going to do this? Well, the first thing we're going to do is we're going to put our carbons on the paper and we're going to put them in the middle. Now the hydrogens have got to go around the outside. The hydrogens can't be in the middle. So we could go 1, 2, 3, and then 4 hydrogens. Problem is that's not symmetrical. We've got 3 on the left, we've got 1 on the right, and that's not what we're after. So what we need to do then is find a way to do this symmetrically. So we're going to put our carbons in the middle, and then we're going to spread our hydrogens 2 on each. Again, guys, up and down and left and right does not matter. Just get them on the paper. Okay, so step number 2 is to count electrons. Remember that carbon has 4 from our previous drawings. Times 2 is 8. Hydrogen has 1 times 4 is 4, which gives us a total of 12. Okay, so now we need to count the ones that we've already used. So we remember that each line counts as 2 electrons. So we've got 2, 4, 6, 8, 10. So we have already used 10 electrons. That leaves us with 2. Okay, so now we've got to figure out where to put these 2 electrons. Well, guys, you can't do this. You can't put them on hydrogen because hydrogen can only form 1 bond. It only has an s orbital, so hydrogen's done. When hydrogen forms 1 bond, it is full. It doesn't obey the octet rule. It's the only atom that doesn't. So where are we going to put these electrons? Well, the only place that we can put them is on the carbon. Now, guys, what we don't do is split them up. We keep them together. And you're going, wait a minute, if we split them up, we could put 1 on each and that would be symmetrical. And that's true, but the electrons stay together in pairs. So now we've got this. So that would be step number 3, and we've put on the paper the unused electrons. So now we need to check the octet rule. Remember, hydrogens don't follow the octet rule. So 1 bond and hydrogen's done. So those guys are good. So now let's look at carbon. So this carbon over here, again, guys, don't draw these circles, but I will so you know what I'm looking at. That carbon has got 2, 4, 6, maybe drawing dots isn't best. So it's got 2, 4, 6, 8 electrons. So that guy's good. But now if we look at this carbon's got 2, 4, 6 electrons, but it doesn't have 8. So now we have an example of a carbon that has not fulfilled the octet rule. So what are we going to do? we can't just put on more electrons because we've only got 12 to work with. So how can we get more electrons on this carbon? And guys, the answer is we're going to take these 2 electrons right here and we're going to push them into the middle and we're going to create another bond. So what we do is we take an eraser and we erase these electrons and we move them into the middle, and we just created what is called a double bond. Now guys, some of you are probably scribbling right now because you've been taking notes in pen. Guys, when you do the homework, write big and do the stuff in pencil. Okay, so now let's take a look at the octet rule. So now we've got this carbon, and that carbon has got 8 electrons, and we look at this carbon, and that carbon has got 8 electrons, and they've both now fulfilled the octet rule. So the last thing we need to do then is we need to do the shared and lone pairs. Remember guys, we only do shared and lone pairs around the central atom, but now we've got 2 central atoms. So all you got to do is pick one or the other, and it doesn't matter which one you pick, the answer is the same. So let's pick the one on the left. So the one on the left has got 1, 2, 3, 4 shared pairs and 0 lone pairs of electrons. Now guys, notice if we'd chosen the carbon over here on the right, the answer would be the same. 4 shared and no lone pairs. Okay, so now we've got 2 of these done. Let's do a couple more. We will pick up the pace a little bit and dig into the interesting bits. So moving along then, the next one that we're going to do, NO3 minus 1. So here we go. First thing we've got to do is we've got to get these on the paper and we've got to spread them out and make them symmetrical. So to do that, we're going to put a nitrogen. I'm going to draw that a little bit higher just so it's a little higher on the board. We've got our nitrogen and we've got our 3 oxygens. Okay, so now we need to count valence electrons. We remember that nitrogen is 5. We remember that oxygen is 6 times 3 is 18. Now what about this minus 1 charge? Well, what do we do to give something a negative charge? And the answer is we add electrons. How many electrons? 1 electron. So that negative charge gives us a bonus electron for a total of 24. Now you'll notice that we already have 6 on the board, right? 3 bonds, 2 each, that's 6. That leaves us a total of 18 electrons. So now we just need to get these 18 electrons on the paper. So we're going to go 1 and 2, 3 and 4, 5 and 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Like so. So somebody in the audience may be saying, someone in the class may be saying, well, wait a minute, can't we just put some electrons on the nitrogen? Sure, absolutely. It doesn't matter where you put them. So long as you are obeying the rules where you don't put extra electrons on hydrogen and you fill the halogens first, it doesn't matter where you put them, so long as you're not putting more than 8. So let's just leave those electrons on the nitrogen then, and we'll let that be okay. Okay, so now we need to check the octet rule. Oxygen, all good with 8. Oxygen, all good with 8. Nitrogen, all good with 8. Oxygen, not good. That guy's only got 6. So we need to figure out a way to give him more electrons. Again, as we just learned, we'll take 2 of these electrons off of the nitrogen. We'll move them into the middle, and we'll create a double bond. This then forms the NO3 molecule, and you'll notice now that everybody has a full octet. So now we just need to do shared and lone pairs. Obviously the nitrogen is in the middle, and there's 1, 2, 3, 4 shared pairs and 0 lone pairs on that central nitrogen. Okay, so we've got one more to go. This one's kind of fun. Carbon monoxide, of all things. So the first thing we need to do is get everything on the paper. We're going to go carbon, we're going to go oxygen. All right. So now we need to count electrons. Carbon 4, oxygen 6, total of 10. We've got 2 on the screen. That's that single bond. That leaves us 8. So let's spread these out. And guys, it really doesn't matter how you do this. You could go 1, 2, 3, 4, 5, 6, 7, 8. That's fine. If you wanted to, you could go 1, 2, 3, 4, 5, 6, 7, 8. That's fine. If you wanted to, you could even go 1, 2, 3, 4, 5, 6 and put 2 on the carbon. It really doesn't matter. You're always going to end up in the same place once you're done. So with that said, I suspect that most of you probably would have spread them out evenly, which is always fine. So we'll do this, and now we've got the 8 electrons on the paper. So now we need to check the octet rule. And as we check the octet rule, we see that this carbon only has 6. So what are we going to do? Well, we're going to take a pair of electrons off the oxygen, and we're going to move them in there, and we're going to create a double bond. Now checking again, this carbon has got, this carbon's got 8, so it's all happy. But now we look at this oxygen, and this oxygen's only got 6. That's not going to work. So what we need to do then is we need to take a pair of electrons off the carbon, and we need to move it into the middle. And now both of these atoms have 8 valence electrons, and we just created what is called a triple bond. So carbon and oxygen are triple bonded together in carbon monoxide. And guys, that's the maximum. There cannot be a quadruple bond. It's either single, double, or triple. So now let's do our shared and lone pairs. Again, it doesn't matter which one we choose. We've got 1, 2, 3 shared pairs, and we've got 1 lone pair of electrons around this central atom. If we chose oxygen, the answer would be the same. Okay, so guys, there you have it. That's drawing Lewis dot structures. Now, here's the trick. Over the last 15, 20 minutes or so, you've watched me draw a series of Lewis dot structures. Again, there's a rhythm to this. We're following the steps. But guys, frankly, right now, the only thing that you know for sure is that I'm good at these. It's time for you to get to work on these. The answers are available online. They're also posted at the front of the room. You're certainly welcome to work with the person that is sitting directly next to you. Guys, please do not get up and form bigger groups. We are going to be careful about social distancing and contact tracing. But guys, let's get to work. Let's spend the rest of the time that you have in class working on these. When you need help, please feel free to get a hold of Miss Call, or certainly you can reach out to me as well. But guys, please, please, please make sure that you get this done before I see you before you have class next, because everything that you're going to learn in class next time builds directly on the stuff that you just learned today. And again, this is a skill that you have to possess. So make sure that you get the practice that you need. Guys, have a wonderful rest of your day. Know that I miss you guys like crazy. I cannot wait to be out of quarantine. They say that December 9th I will be back. That's a Wednesday, so you won't see me. But then, guys, on Thursday the 10th, I'll be back. So, guys, yeah, do well with these. Again, do them in pencil. Write big. Grab another sheet of paper, because you don't want to be doing these in cramped spaces. It just makes them a lot harder than they need to be. So dig in and enjoy.